Hello, everyone. This is going to be a week 4 review and kind of explain everything, implement some new stuff. Yeah. So this week we kind of focused on just some of the basic spawning, mark for delete. We expanded the polygon component. Um, and yeah, so what we'll do is we'll kind of go over the polygon component. So let's begin. So obviously, if we go to our polygon.js in our engine, we now implemented this points. Or now we can actually, just like our color, we can input the points in order to draw specific shapes now. So, for example, what we did was that inside of our laser game object, we made a rectangle. But that was okay. There's some things that shapes that we may want to create that aren't so obvious. And one example could be something as simple as in a rectangle game object. What we want is we want points, and let's make a octagon. So you would do new vector 2, and what do you do now? Well, you don't really have a way to determine the points. So rather than trying to Google it or um, manually try and look at it, let's update our polygon.js file to create a new static method called generate n-gon. And it's going to be as simple as this. Let's go to PowerPoint. It's this one. Yep. All right. It's as simple as this. When given some sort of shape with n sides or edges, we calculate the angle of each from the edge to edge. So from this edge to this edge, we calculate the angle, and we calculate the points that it would be by using cosine and sine. Cosine being the x value, sine being the y value. So with this rectangle, for example, or square, if n equals 4, what we would do is we would have 360 degrees, which is the full rotation, and divide it by 4. That means each area or section, quote unquote, is 90 degrees. So if we iterate incrementally from 90 degrees each time, we can get each individual point. So as you can see, our zeroth, or our zero implementation, or implementation at 0, would be cosine 0 sine of 0, which would be 1, 0. Then when we do Then when we add 90 to it, which is determined by 360 divided by the number of sides, then we get cosine of 90, which is 0, sine of 90, which is 1. And then we do that again by adding 90 for the 180 degree, and then adding 90 for 270. So this is kind of the whole general idea. So for example, if we did n pentagon, we would do 360 divided by 5, and then we would just iterate until all ends are completed for each individual point. So the general structure we kind of want to do is we first want to do let's do this. So given some n, the general stuff we want to do is we want to store vectors into a list. We want to loop through n based on some angle determined by n. We want to use cosine and sine to determine the position of the vector. And this is kind of the general idea of what we want to do. So let's do that. So first thing we want to do is just let's make a simple vectors array. And then we need to determine it based on some angle. So let's say let let's say angle step equal 2 times math.pi, which is the full 360 degrees, and divided by n. It is important to note that everything we do will need to be in radians when doing calculations like this. So now we have the angle, and now we just need a loop through n. So we do a simple for loop. At I equals 0, I is less than n, I plus plus. And now we determine our angle by saying that angle equals I, our current iteration, times the angle step. And now we just say let x chord equal math dot cosine based on our angle, and let y chord equal math dot sine of our angle. And now we just do vectors dot push new vector 2 x chord and y chord. And then at the very end, so right here, we do that. And now outside of this for loop, we return vectors. So now if we go to our rectangle game object and we do console.log polygon generate n-gon, and let's give it 4. Let's see what is produced. So we have our array, and it's kind of so one thing to see is that we have this really small number, and it's in scientific notation, so it's 6.123 e to the negative 17, which is 0.1, something like this. Oh, this one more 0. But it is a very small number, so we don't really. It's fine like that, but I don't really want to have those very minuscule numbers that should just be 0 and is literally just so small it doesn't even matter. So let's just count for it to make it 0 when it's this long. Usually these are called epsilon values or like delta values. So, but I usually do epsilon, and what we can do is we could do scientific notation with 1 e to the negative 10. And it's basically saying 0.123456789. I think it's just saying like this, basically, this number. So what we want, and I should say this is equivalent to that. But what we want is we say, hey, if our x chord is less than our epsilon value, we just set it equal to 0. And we do the same thing for y coordinate. It just makes it easier to read and also easier to have points, especially when we're getting into higher degrees of shapes. So now when we look, what should happen is that it should just be very simple 0 ones. But there's an issue. X chord can be both positive and negative values. So in order to account for this, we need to assign math.absolute around x chord and math.absolute for y chord as well. And now when we look at it, now we have our 1, 0, 0, 1, negative 1, 0, 0, negative 1. So now if we just go in and we do, so now we can go into our laser game object. Rather than having this, let's just say polygon.generate n-gon with 4 sides. And now when we look at it, the exact same game, just way simpler code, and now we can actually expand upon this. Say we want the triangle game object to stick as a triangle, but use what we currently have rather than using the default value. Well, we could do points, polygon dot generate n-gon 3. So now all these triangles will have use the points as the polygon generate n-gon function rather than the default. And you see it's a little weird now. Obviously, it's now generating in a sense that in not the right direction. So we could implement the rotation in our transform, but I think we should leave that up to in class because there's a couple things associated with that that will naturally flow. So we'll just do a temporary solution of polygon, and rather than having just n, we can also have a start angle, which we can just assume it's 0 if it's not inputted. And we need to make sure that and we need to make sure that it's in radians. So we'll input it in degrees because that's more natural to what we see. But we need to make sure that we convert it into radians, which is as simple as doing your start angle times that by math.pi over 180. It is basically degrees. Oh, did I do? Yeah. So it's basically start angle times degrees over it's your degree. So your start angle is your degree, your math.pi is your radian value, and the 180 is also a degree. So your degrees cancel out to give you in pi, in terms of pi, which is radians. And now we just add this to there, and now we can kind of experiment with this. So in our start angle for triangles, let's have a start angle of 90 degrees. So now, so one thing to note is that what happened is that it took this triangle right here and rotated it 90 degrees. When you rotate down, you rotate clockwise, because your y is inversed. At least I think that is the case. So if we rotate 270 degrees, then it should now be up and normal. So now your triangle's all right. But now let's try and make it an octagon. If we, rather than finicking with where coordinates are and all that stuff, let's just now type in 8, and now they're octagons. And now you can kind of go on and continue with that. Let's do 100 to make a circle. Now you've made circles. So yeah, we continue with, let's continue with triangle on those, but now the next kind of thing we did is we did the vector multiplication. So if we look at, let's just do a quick review of that, and then just kind of see how that stuff happens, and then we can continue with one last thing that coding wise. So for scalar multiplication, it is just a vector times some constant n, and it's usually called it's called times in the Unity API, and it's just a new vector where you take your x component of your vector and you times by the constant that n value, and you do the same thing for y. So when we look at this, it would be 2. So vector 2 comma 5 is multiplied by 7. You would just do 2 times 7 and 5 by 7. And in this case, it would be 14 comma 35. I'll let you do the rest. Generally speaking, this is very, it's relatively simple compared to something like dot product or cross product, which would be explained later. So as you can see, you do 2 times 7, which is 14, and then 5 times 7, which is 35. Same thing with 6, 3 is multiplied by 4, and then same thing with 4, 8 is multiplied by 0.5. This is basically just extending or reducing the length of the vector because it's still in the same direction, it's just longer or shorter. Now, component-wise multiplication, this is usually called scaling, and it's just it's very similar to scalar multiplication. It is just you're with two vectors now instead of just a vector and some constant number. So it is just vector 1 x component times vector 2 x component, and then vector 1 y component times vector 2 y component. So in this first example, it's just be as simple as 2 times 1, comma, 5 times 2, which would equal the new vector 2, comma 10. So if we continue on with that, you see that it's 2 comma 10, and then there's some examples, further examples, where you do 6 times 6, which would be 36, and then 3 times 6 would be 18. Same thing with the 0.5. Now, dot multiplication is the most important, I would say, out of the ones that will be covered today. Unity API calls that dot, and it is vector 1. It is it's very similar to component-wise, but rather than having a separate vector, you add the x and y components together of the component-wise multiplication. So it's vector 1x times vector 2x plus vector 1y times vector 2y. When these vectors are normalized, or when x and y are the sum of x and y equals 1, if the dot product is approaching 1, it means the vectors are in the same direction or parallel. Dot products approaching 0 means the vectors are orthogonal, which are 90 degrees. And then dot products approaching -1 means the vectors are in the opposite direction, but parallel as well. Dot products also project a vector onto another, like a shadow. So say, for example, you have two lines, and you want to see how far one line is if it was on the other line or on the other vector. Well, if you shine the light on it from top down, you would kind of see the shadow of one of the vectors on the other, and that's kind of what we call the projection of a vector onto another. Here are some examples. So if we did this before, where you do 2 times 1, then this time you add 5 times 2, and this would equal 2 plus 10, which would equal 12. So you could do the other two, and here's what I got, where you do 6 times 6 plus 3 times 6, that would be 54, and then 48 multiplied by 0.56 gets you 50. This is kind of the overview of vector multiplication we discussed in class. This will be explained further, and we will also go into cross product. Now, one thing we did go through is we talked about instantiating and deleting objects inside of the game. So I just wanted to expand upon that further and kind of determine what do another example of it. It's probably the best way to describe it. But before we do that, one thing I wanted to do is look at the delta time value. Delta time is very critical because if you have two games running at different frame rates, one at 60 frames, one at 120 frames, what will happen is that, say you move 1 foot in a game, you move 1 foot for every frame. Well, if one's frame rate is higher, then one will be moving faster. So we want to normalize that by doing some math in it, which will be discussed further in class as well. but we want to get used to doing stuff, multiplying by this delta time value. So let's make a new game object, kind of doing instantiating and deleting like an enemy spawner. So let's make a new file, and let's call it enemy spawner game object. And we do class enemy and then spawner game object extends game object, and we just have a constructor where we do a couple things. Since we're going to delete this, we want it to have a polygon component and then some sort of scale because of that as well. But first, we always need to call super, and let's call this enemy spawner game object. And now we do this dot add component new polygon. And what we want is let's do the, oh, it needs to be this, fill style, and let's make it yellow. And let's make the points, and let's make it a circle-like, so we can do polygon dot generate n-gon, and let's do 32 and 0. And now we need to scale it. So now we can do this dot transform dot scale equals new vector 2. And then we do 25 comma 25. And then what we want to do is then we need to add a enemy spawn controller. So this dot add component new enemy spawn controller. And we need to now create that. So now when we go into components, we do enemy spawn controller.js class enemy spawn controller extends component. And this is where then we have our start and our update. Okay. Similar to how we did a fire, what we'll do is we'll do this dot next enemy spawn frame equals 250. So let's make it so that it is every 250. And what we'll do is we will say, hey, let's also start on frame 250 internally so that it spawns one immediately. So we don't have to wait 250 frames. So now what we do is we do something similar. We do this dot frame plus plus if. So now if we see if the frame is greater than our next frame spawn, then we spawn the enemy. So now we do n dot currency dot instantiate. And let's do our new triangle game object. And my triangle game object is different than yours. So if we go into here, we see that we input an X speed and Y speed. So now we go into that end. Now let's do X speed and Y speed, but let's make it a little different. Obviously, not all enemies are the same. So let's do a little bit of math dot random. And what we want to do is we want to have a range of 30, and we want to start at negative 15, so it can kind of go a little bit backwards. So it's not all in one direction. It's 360 degrees. And now we do that the same with this. Now with our instantiate, though, we have to give it a position. And the way we would do this in this specific instance, it just represent the game object dot transform dot position. Basically, we're going to spawn these enemies on side of the spawner so that it and then the spawners will then, or the enemies will then spread out in a random direction. So Now with this, now we need to reset the frame. Oh, let me kind of show you all the code here so that you can see it all. And then what we want to do is then set next enemy frame equals this dot frame plus 250. So now let's go into our scene. And let's do this. Let's spawn in a new enemy. This dot instantiate new enemy spawn game object. And let's do new vector 2. Let's do 500, 500. Now it won't work because inside of our HTML, we are not adding any of these. So what we will need to do is we'll need to copy and paste. Instead of laser, it's going to be the enemy spawner game object. And it will be the enemy spawn controller.js. Now, hopefully, okay, there's a bug that we have where the position of only spawning one and it's following that. Do we have any counselors? No. Okay. Let's go look at this. So inside of our enemy spawner game object, we have an enemy spawn controller in the position. And we do this dot frame dot transform. So then we establish that. I think the best way to debug this is to go into here and look to see what's happening inside of our source. So inside of here, inside of, let's look at components and let's look at your enemy spawn and let's look at this and we just reload. Okay. So we go over and saying this dot frame is greater than that. We instantiate a new triangle game object referencing the new position. I don't fully know what's happening. Let's get rid of this to see if it's still moving. Nope. So for some reason, we are. Oh, and it's because we need to do the dot clone. It is inheriting. Yes, I think. Yep. Okay. So just like something similar in class thought, what happened? What was happening is that it was saying, "Hey, you're referencing this." We just it continuously it basically connected the position of the triangle and the spawner, and that was the main issue with it. Now we kind of have the spawner where it's kind of shooting out a bunch of random stuff. And let's say we only want 5 to spawn and then it deletes. What we could do is we could have a this dot spawn counter equals 0. Inside of here, we do this dot spawn counter plus plus. And then outside of here, we say if this dot spawn counter is greater than 5. So it'll spawn 6 then. What we want to do is we want to do something similar to our laser controller. where we do this.gameObject.destroy. So we can just copy and paste this. So now it spawns 1, 2, 3, 4, 5, 6. No. Let's see. 1, 2, 3, 4, 6. Oh, yep, we have a bug. Let's go check this out. Let us see what's happening in here. So let's open up the game and let's do inside of our source. Instead of doing it on the frame update, we do it in here and we restart. So spawn counter equals 0. That's why we misspelled counter. Okay. So now if we remove this, we reload this. 2. So it spawned 1, 2, 3, 4, 5, 6, and then it destroyed itself. Of course, we can adjust the movement speed of these, so we could do times it by 50 and move it to -25, and that should increase the speed. But it is going to be, since we're going from a negative and a positive to a positive, we'll always have the chance of doing something very small, like 0.001 as a randomized number. So there's a couple ways to go get around this. You could always do positive numbers. So say, for example, you could go from 25 to 100, and then you do a 50-50 on if it's greater than 1 or greater than 0.5 or less than 0.5 to see if it's positive or negative. I could demonstrate that. So say, for example, we could do something like if random speed equal math.random times, let's say 75 plus 50. What we could say is then if math.random is greater than 0.5, random speed times equals -1, and then we just use random speed. So if it generates something bigger than 0.5, which math.random generates from 0 to 1, then we say, hey, make that negative, and then you would have to do that for your y speed as well, and then you would just plug that in. So yeah, we could do that. Let random x, and then we do this again, but for y. There may be a simpler way to do this, but this is the most intuitive. For me, anyway. And now we just use random x speed, comma, random y speed. And now all those should be way faster. And as you can see, they're going in, generally speaking, different directions. And then say you wanted more spawners in your scene. Now all you would need to do is copy and paste this line and just change the position. So say I wanted 4, one at like 250, 750, 100, 100, and then like 200, 500. I have all of these spawning stuff randomly. And now once you get collisions, you have to get a randomized, generated game to survive. It's almost like asteroids, um, if you know what asteroids is. So that's kind of all I wanted to talk about today. If there are any questions, comments, you could always email me at this. My email should be on the syllabus otherwise. Or you could also talk to me after class.